Water Resources Engineering 2, Unit 1, Gravity Dam. Principal and shear stresses. So, the vertical stresses intensity PB maximum or PB minimum determined is not the maximum direct stress produced anywhere in the dam. So, the maximum normal stresses will be the major principal stresses that will be generated on the major principal plane when the reservoir is full. So, the vertical direct stresses is maximum at the toe as the resultant nearer to the toe. To study the principal stresses that will be developed near the toe. So, let us consider a small element A, B, C near the toe of the dam. So, the element is so small that the stresses intensity may be assumed to be uniform on its face. So, the face of dam, so this is downstream, will act as a principal plane because the water pressure P dash acts at the right angle to the face, and also there is no shear stress acting on this plane. Since the principal planes are at right angles to each other, so the plane BC drawn at right angle to the face AB will be the second principal plane, and that is the major principal plane. So, let the stress acting on this plane be sigma, considering unit length of the dam. So, the force acting on the face AB, BC and CA are P dash into ds, sigma into dr and PV into dB respectively. Resolving all the forces in the vertical direction. So, P dash ds sin alpha plus sigma dr cos alpha is equal to PV into dV. But now from the triangles, the ds upon dV, that is the sin alpha, and dr upon dV, that is the cos alpha. So, P dash, put the value of ds and put the value of dr. So, ds is equal to db sin alpha and dr is equal to db cos alpha. So, put here. So, then the p dash. So, now that comes out the p dash sin square alpha plus sigma cos square alpha is equal to pv. So, sigma is equal to this is the pv 1 upon cos square alpha and minus p dash sin square alpha upon cos square alpha. So, this comes out the sigma is equal to pv sec square alpha minus p dash tan square alpha. So, for sigma to be maximum, so p dash should be 0, that is when there is no tail water. So, sigma is equal to pb sec square alpha. So, sec square alpha always greater than 1, because this is the 1 plus cos square alpha. So, if the value of the any value of the alpha, so then the sec square alpha, that is always more than the 1. So, sigma that is more than or it may be equal to PV. But not exceed the maximum allowable compressive stress of the dam material. If hydrodynamic pressure, consider PE dash, exerted by the tail water during an earthquake moving towards the reservoir, is also considered. So, then the net pressure on face AV will be P dash minus PE dash, because the effect of this earthquake will be to reduce the tail water. So, sigma at toe is equal to PB sec square alpha minus P dash minus PE dash tan square alpha. Similarly, the sigma at heel, that is the PB sec square alpha minus P plus PE tan square alpha, but this alpha is considered as a phi at the heel. So, this will comes out the sigma heel is equal to PB sec square phi minus P plus PE tan square phi. So, here this phi is the angle at upstream phase that will mix with the vertical. Okay. So, for upstream phase, the sigma will be always less than the P, and hence P will be the major principal stress and sigma will be the minor principal stress at the heel. Then the shear stress. So, this shear stress on the horizontal plane near the toe. So, resolving all the forces in horizontal direction. So, comes out the sigma dr sin alpha minus P dash ds cos alpha is equal to tau into dV. So, put again the value of the dr and ds. So, that will comes in terms of the dV. So, here is comes out the sigma, sorry, this is the tau and this represents that is the tau 0. So, tau 0 is equal to sigma minus P dash sin alpha cos alpha, and substitute the value of sigma in this equation. So, tau 0 is equal to Pb sec square alpha minus P dash tan square alpha minus P dash into sin alpha into cos alpha. So, tau is equal to Pb sec square alpha minus P dash 1 plus tan square alpha into sin phi cos phi. So, this Pb minus P dash sec square alpha into sin alpha cos alpha. So, it will comes out the tau 0 is equal to Pb minus P dash tan alpha. If neglecting tailwater, then the P dash is equal to 0. So, then the tau is equal to Pb tan alpha. If the effect of hydrodynamic pressure produced by an earthquake moving towards the reservoir is also considered, so the equation at the toe is that tau 0 is equal to Pv minus P dash minus Pe dash tan alpha. So, similarly, the shear stress at heel, the tau heel is equal to minus minus Pb minus P plus Pe tan phi. So, this negative sign shows the direction is reversed. The next article of this gravity dam, that is the very important, the elementary profile of a gravity dam, and it is also known as the theoretical profile of gravity dam. So, if we consider only hydrostatic force, so the elementary profile will be triangular in section, having 0 width at the water level where the water pressure is 0, and a maximum base width is B, where the maximum water pressure acts. Thus, the section of the elementary profile is similar to the shape of hydrostatic pressure distribution diagram. So, for reservoir empty condition, a right angled triangular profile will provide the maximum possible stabilizing force against overturning without causing tension in the base. So, this is so because the bed of the dam acts at a distance b by 3 from the upstream face and is closer to it. So, the force acting on the elementary profile of a gravity dam, here the three main forces are acting. The first one is the self weight of the dam. So, self weight of this triangular portions, and here is consider the 1 meter length of the dam. So, the weight of the dam, that is the area of this triangle. So, means 1 by 2 B into H into 1 meter into the density of the material. So, this is the SC into gamma W. So, here SC, this is the specific gravity of the dam material, which will generally taken as or the vary in between of the 2.2 to 2.4, and gamma W, that is the means the weight density of the water. So, this is the 9.81 kilonewton per cubic meter, and the B and H, this is the base width and the height of the dam, and this W is act vertically through the centroid of this triangle. So, at a distance of the B by 3 from the heel or the 2B by 3 from the toe. The other force, that is the water pressure. So, this is the hydrostatics. So, means this is the 1 by 2 gamma W into H into the H. So, this is the area of this triangle, again into the 1 into 1. So, then it will act H by 3 from the base, and the third one, this is the main important forces, this is the uplift pressure. So, this is the area of uplift pressure diagram. So, now here is consider the uplift pressure intensity at the heel, that is the C gamma W into H, but at the toe here is no water. So, then the area of this triangle uplift pressure diagram, the area of uplift pressure diagram. So, this is the 1 by 2 B into C gamma W into H, where the C, this is the uplift pressure intensity factor, and this force is acting at a distance of B by 3 from the heel in upward direction. So, base width of the elementary profile. So, base width of the elementary profile is to be found under these two conditions or two criteria, that is for the minimum base width. So, when the reservoir is empty, so for no tension to develop, the resultant should act at the inner third point, that is at A, and for the reservoir full condition, for no tension to develop, the resultant R must be passes through the outer third point, that is the B. So, that is for the no tension. Okay. And the the dam is safe in slidings. So, then this is the frictional resistance always more than the horizontal forces. So, base width with no tension. So, when the reservoir is empty, for the no tension to develop, the resultant should act at the inner third point is A, already discussed in the previous slides. And for the full reservoir condition, suppose the R is the resultant of all the forces acting on the dam. So, for the no tension at the heel, the resultant must pass through the outer middle third point, that is the B. So, the maximum value of the eccentricity E is taken as the B by 6, and when the resultant R passes through the point B. So, for the no tension, so taking the moment of all the forces about outer third point, that is the B, means W into B by 3 minus U into B by 3 minus P into H by 3 is equal to R into 0. So, W minus U into B by 3 is equal to P into H by 3. So, put the value of the W and P. So, this is the W minus U upon P is equal to H by B. So, put the value of W and U. So, it will comes out the B square in bracket of SC minus C is equal to H square. So, that this B should be more than or equal to that is the H upon under root of SC minus C. So, if B is taken equal to or the greater than the value of the equation B is equal to the H upon under root of SC minus C, then no tension will be developed at the heel with full reservoir condition. Now, if the value of the taken as the C is equal to 1, so then the full uplift pressure. So, B should be more than or equal to the H upon under root of SC minus 1, or if there is no uplift when the reservoir is empty condition. So, B is equal to the H upon under root of SC. So, for the no tension in the elementary profile, now to determine the base width by the equation of H upon under root of SC minus C, or now putting the value of the C is equal to 0. So, then this will be comes out the when the reservoir is empty condition. So, you have any problems, so you can contact me at any time. So, thank you very much.